Hey, what's up, everyone? This is Sam with This Week in Machine Learning and AI. I'm happy to share with you the recording from our second TWiML online meetup. This month, we discussed the paper Learning Long-Term Dependencies with Gradient Descent is Difficult by Yoshua Bengio and company. This is a really interesting classic paper that explores one of the key challenges with training recurrent neural networks, the vanishing gradient problem. It looks at some alternative approaches and ultimately sets the stage for future advances in the field like LSTM and GRU networks. A huge thanks to our presenter this month, Nikola Kucherova. Whatever you do, be sure to tune into our next meetup live. We cover new and classic papers in machine learning and AI, and we'd love to have you join us. To register, visit twimlai.com/meetup, where you'll also find information about our next event. Enjoy the video and catch you next time.
Okay, so hello everyone. Today I will be talking about a paper called Learning Long-Term Dependencies with Gradient Descent is Difficult by Yoshua Bengio, Patrice Simard, and Paolo Frasconi. So very quick overview. First, a little bit of introduction, what the paper is about. Then the minimal task that is going to illustrate the problem, analysis, some alternative approaches to gradient descent, experimental results, and the conclusion. So just a few words about me. I'm studying information technology in Sydney, so I don't actually have any background in machine learning, but it's an interesting area, so I'm trying to learn more. I'm enrolled in the machine learning course by Andrew Ng, and I definitely did learn a lot when I was preparing for this presentation. So if you want to learn yourself, I highly recommend signing up to present a paper. So recurrent neural networks are very good for mapping input sequences to output sequences. However, there are some issues. Types of problems that RNNs can solve are recognition, for example, speech recognition, production, which could be stuff like text generation or machine translation, or prediction, which could be stock market movement or consumer behavior. So a lot of things that involve sequences. Difficulties have been reported in training recurrent neural networks that perform tasks where there are long-term dependencies that need to be taken into account. And increasing durations of the dependencies is causing problems for gradient-based learning algorithms. So this paper looks into why this problem actually occurs, and there are some trade-offs exposed between learning efficiently by gradient descent and latching on information for long periods of time. So based on understanding of this problem, there are some alternative approaches to gradient descent that are considered. So training neural networks.
Nicola, before you continue, I think it's the video panel is covering some of the slides on your screen. Mm-hmm. And it's obscuring the right-hand side there. If you can minimize that or move it, it might be helpful for folks.
Oh, yeah, okay.
Okay, great, thank you.
So, training recurrent networks, applications that I mentioned before require a system that is able to store and update context information, and information computed from the past inputs can be used to produce desired outputs. And this is something that recurrent networks are very well suited for because they have an internal state that can represent context information. So recurrent networks are able to keep information about past inputs for period of time that is not fixed, and it depends on the weights and the input data. And so we can transform input sequence into an output sequence while taking into account contextual information in a flexible way. And in this paper, we are going to focus on discrete time systems. So learning algorithms that are used for recurrent networks are usually based on computing the gradient of a cost function with respect to the weights of the network. Some algorithms that are used are back propagation through time, forward propagation algorithms. Another algorithm that was proposed for training constrained recurrent networks with dynamic neurons only have one incoming connection from the input layer. So these networks can only deal with limited storage, only have limited storage for dealing with general sequences. So their representational power is quite limited. So what actually are long-term dependencies? A task displays long-term dependencies if prediction of the desired output at time t depends on input presented at an earlier time. So for example, it means that the gap between a place where the relevant information occurs and the place when where this information is needed is too large. So recurrent networks can outperform static networks that don't have recurrent connection in most cases, but are more difficult to train optimally. And that's because their parameters settle into suboptimal solutions that take into account short-term dependencies, but not long-term dependencies. And it was found that backpropagation was not sufficiently powerful to discover contingencies spanning long temporal intervals. So this paper presents experimental and theoretical results that are trying to look into this problem a little bit more. So for comparison and evaluation purposes, we have basic requirements for a parametric dynamical system that can learn to store relevant state information. The first one is ability to store information for an arbitrary duration. The second one is resistance to noise, which means fluctuations of the input that are random or irrelevant to predicting a correct output. And the third one is trainable system parameters in reasonable time. So the minimal task was designed as a test that must be necessarily passed in order to satisfy the three basic requirements. A parametric system is trained to classify two different sets of sequences of length t. And for each sequence u1 to ut, the class C u1 to ut depends only on the first L values of the external input. We suppose that L is fixed, and we allow sequences of arbitrary length where t is much larger than L. So L is basically a very small subset of t. So the first condition from the previous slide would say that this problem can only be solved if the dynamic system is able to store information about the initial input values for an arbitrary duration. The second condition means that the values of ul plus 1 to ut, which is the rest of the sequence, those values are irrelevant for determining the class of the sequences. So these values are basically noise, but they may affect the evolution of the dynamic system and eventually erase the internally stored information about initial values of the input. So the system needs to be able to robustly store information in a way that it cannot be easily deleted by events that are not related to the classification criterion. One term that I would like to define here is information latching. It's the long-term storage of definite bits of information into the state variables of the dynamic system. And so the third condition was learnability. And there are two computational aspects involved in this task. Firstly, it's necessary to process U1 to UL in order to perform classification. And secondly, it's necessary to store such information into a subset of state variables of the dynamic system for an arbitrary duration. And for this task, the computation of the class doesn't require accessing state variables. So these state variables that can store information don't need to affect the evolution of the other state variables. So a simple solution here would be a system that would have two subsystems. One would be the latching subsystem, and that one would be fed by a subsystem that can compute information about the class. So we are interested in assessing learning capabilities on this learning latching problem. And we want to do it in a way that is independent of any specific problem of classifying U1 to L. So in this paper, we are only going to focus on the latching subsystem. And in order to train any module feeding the latching subsystem, the learning algorithm should be able to transmit error information, such as gradient descent, to the previous module. So instead of feeding a recurrent network with the input sequences defined previously, we will only use the latching subsystem as a test system, and so we need to reformulate the minimal task. So the new task, the new system will have one input, ht, and one output, xt, at each discrete time step t. The initial input for ht, where t is smaller or equal to L, are values which can be tuned by the learning algorithm. And for t that is larger than L but smaller or equal to t, ht is a noise. So optimization is based on the cost function here, where p is an index over the training sequences, and dp is a target of plus 0.8 for sequence of class 1 and minus 0.8 for sequence of class 0. So in this formulation, ht, where t is 1 to L, represent the result of the computation that extracts class information. And learning ht directly is easier than computing it as a parametric function of ht with parameters ut and theta, and of the original input sequence, and learning the parameters of theta. So if ht cannot be trained as parameters in the system because of the vanishing gradient, they clearly cannot be trained as a parametric function of the input sequence in a system that uses a trainable module to feed a latching subsystem. And the ability to learn the free input values h1 to hl is a measure of effectiveness of the gradient of error information that would be propagated further back if the test system were connected to the output of another module. Before I go to another section, are there any questions?
I've got a question. Where did they talk about where the DP value of 0.8 comes from?
No.
Okay, that seems a very specific, magic number to just stick in there without any kind of elaboration.
It's defined here, but there is nothing else.
Okay. Any other questions before we move on? There was a question in Slack, DP, the DP represent the targets. Remind us what the DP
stands for specifically?
DP is the target for
Yeah.
plus 0.8 for sequence of plus 1 and minus 0.8 for sequence of plus 0.
Okay.
Any other questions? Okay.
All right.
So, a simple recurrent network candidate solution. Experiments on this minimal task that was defined were performed with single recurrent neuron. This is the neuron in figure A. And this recurrent neuron can robustly latch one bit of information represented by the sign of its activation. And storing is accomplished by keeping a large input for long enough time. Small noisy inputs cannot change the sign of the activation of the neuron, even if applied for an arbitrarily long time. And so the robustness essentially depends on nonlinearity. And recurrent weight W, which is in the picture, is also trainable. And so the solution for T is much larger than L, requires very large weight. So the larger the weight, the more robustness against noise. And here are some experimental results for the minimal problem. Figure 2a is density of training convergence with respect to the initial weight W0 and the noise variance S. So the W0 is the horizontal axis, and the noise variance is S, which is the vertical axis. And white means high density. So as we can see from this picture, its convergence becomes very unlikely when the noise variance is large in here, or where the initial values of the weights are too small. So this is this part. And figure 2b, frequency of training convergence with respect to the sequence length T, which is on the horizontal axis. Here the noise variance was fixed to 2.0 and the initial weight was also fixed to 1.25. And so here we can see that this task was consisted only on of learning the parameters, input parameters HT, and when T becomes large, it's extremely difficult to attain convergence. So this is a very simple solution where we are only trying to robustly latch on one bit of information about the input, and the gradient descent on the output error fails for long-term input-output dependencies for most initial parameters. And this is solving this minimum task is the basic requirement for being able to transmit error information backwards toward the module feeding the latch unit. There are some other questions.
The question. Go ahead.
What does training convergence density means? I am not entirely sure, but I would say that they tried a few different initial values and just tried which of them would lead to convergence. And the values that were like for the initial weight, if the initial weight is too small, the convergence would be unlikely, but if the values are higher than like certain point, then the convergence is possible. And the same with the noise variance. So training convergence density probably means that in the area where the initial weights were large enough and the noise variance was small enough, the convergence was possible. I hope I answered your question.
Now, Aravind adds in the Slack that the graph looks very zip-esque. Would you like to jump on and elaborate on that at all, Aravind? All right, so going back to the training density, so high chance of convergence. I think the light in that graph, the light part of the graph represents where there's a high chance of convergence. Is that right?
White means high density, yes.
And then another question, L is fixed at 3 for figure 2B. That's a question.
L is fixed at 3 and T is 20 for the first figure. And for the second figure, noise variance is fixed and initial weight is fixed.
And so in figure 2B, we're varying T. But does it say anything about what, it doesn't look like it says anything, at least in this caption, about what L is for figure 2B.
L is T is the length of the sequence, and L is the length of the initial parameters that are necessary for classification.
Mm-hmm. And so we can probably assume that the L length is fixed for figure 2B, but we don't necessarily know what it is here.
Yes.
Okay.
Okay, so learning to latch with dynamical systems. The conditions under which a recurrent network can robustly store information in a way defined in this paper means with hyperbolic attractors yield a problem of vanishing gradients that can be very difficult to learn. So using hyperbolic attractors to latch bits of information can result into one of the two conditions. It's either the system is very sensitive to noise, or the derivatives of the cost at time t with respect to the system activations A0 converge exponentially to as t increases. So this is the essential reason for the difficulty in using gradient descent to train a dynamical system to capture long-term dependencies in the input-output sequences. And this part is has a lot more detail in the paper, but I'm just going to summarize. So when we are trying to store even just one bit of information in a way that is resistant to noise, the gradient with respect to past events rapidly becomes very small in comparison to the gradient with respect to recent events. So it makes using gradient descent on the weights of a network very inefficient. So effect on the weight gradient. Here is an example that is similar to the minimal task. And it shows how the problem with gradient descent can cause problems with training a system that requires robust latching of information. So we have two subsystems, subsystem A and subsystem B. The output of A is being fed into the input of B. And so a good solution for this problem requires B to be able to store information about events detected by A at time 0 with the output of B at a later distant time t used to compute an error. And so if B is not trained enough and it's not able to store information for long enough time, the gradients of the error at t with respect to the output of A at time 0 are very small. And since B doesn't latch, the outputs of A at time 0 have very little influence on the error at time t. On the other hand, if B is trained enough and it's able to reliably store information for a long enough time, the gradients can propagate, but because they quickly vanish into very small values, training A is very difficult. And well, it depends on the size of t and the amount of noise between 0 and t, which is the length of the sequence, but it's generally difficult to train A. Any questions? Okay, so question? Subsystems A and B are not different networks. Okay, so subsystem A, it's exactly the same as the minimal task. Subsystem A is supposed to detect which events trigger latching, and subsystem B is supposed to store that information. And these two need to work together in order for the system to be able to store information about the input sequence and then correctly classify the whole sequence.
Can you go back to the previous slide? So they proposing that that a general solution is to have your the RNN that is to try to divide it up into two subsystems, the RNN that you're trying to get to converge, and then some other system that is able to track the events that the first one detected. Is that?
Yeah, well, in the experiments that they used the network that consisted on just one neuron, so that's just one network, but there are two systems inside the network, I think.
And the one neuron is A, or is the one neuron include both A and B?
Both A and B.
Okay. All right.
Any other questions? Okay. So, alternative approaches. One way to help in training of recurrent networks is to set their connectivity and initial weights, including the constraints on weights using prior knowledge. And there are some other papers where this was accomplished. And the recommendation is that if there is any prior knowledge that is given, it should be used because the learning problem is very difficult. And so the first alternative approach is simulated annealing. It's a global search method, so it's generally very slow. It's a batch learning algorithm. So the parameters are updated after all examples of the training set have been seen. It performs a cycle of random moves, each along one coordinate direction. Each point is accepted or rejected. Exactly how this works is in the paper. I'm just going to point out the main things. So the training stops when some acceptable value of the cost function is attained, when the learning gets stuck, which means that the cost value on the last endpoint doesn't change by more than a small constant, or if a maximum number of function evaluations is performed, and a function evaluation is corresponds to performing a single pass-through network for one input sequence. The second alternative approach is multi-grid random search, which is similar to the previous algorithm. It tries random points. So if the main problem with learning task was plateaus rather than the local minima, an algorithm that accepts only points that reduce error could be more efficient. And this algorithm has this property. And the stopping criterion is the same as for the previous one. Time-weighted pseudo-Newton optimization. So the pseudo-Newton algorithm for neural networks has the advantage of rescaling the learning rate of each weight dynamically to match the curvature of the energy function with respect to that weight. And this is something that we are interested in because adjusting the learning rate could potentially circumvent the problem of vanishing gradient. And this algorithm consistently performs better than standard backpropagation, but it still fails increasingly as we increase the span of input-output dependencies. So this algorithm and the previous theoretical results inspired the time-weighted pseudo-Newton algorithm. And the basic idea here is to consider the unfolding of the recurrent network in time, and each instantiation of weight as a separate variable. But here there is a constraint with that these now separate variables should be equal. And also more details in the paper. I'm just trying to summarize. So are there any other questions? Okay, the next one is discrete error propagation. So far, the analysis suggests that the root of the problem lies in the essentially discrete nature of the process of storing information for an indefinite amount of time. The gradient backpropagated through time vanishes when the system stays in the same stable state for several time steps. So we would like to recover some error information at a time when the input made the system reach that stable state. This algorithm was explicitly designed to propagate discrete error information through units that compute non-differentiable function instead of propagating a gradient through differentiable units. Also more details in the paper. And this approach is not optimal. There are many other discrete error propagation algorithms that are possible, but an important thing to note here is that discrete propagation of error offers interesting solutions to the vanishing gradient problem in recurrent networks.
Yeah, so quick question. When you say, sorry, so you say the approach is not optimal, do you just say that like from a gradient descent perspective, like you wouldn't be able to find a global max if it existed? Is that what you define as like not optimal?
In the next section, there are the experimental results. So I will compare how these algorithms perform.
Okay.
So that should answer your question.
Yeah, there's also some discussion on the Slack around the role that this paper plays in kind of the big picture or the broader trajectory of research for RNNs, and you know, particularly with regards to LSTMs. And I think the comments on the Slack are right on in that what this paper really does is outline this vanishing gradient problem that you talked about earlier and why it's so difficult to train RNNs. And then the LSTM paper, which came like 4 years or so later in '97, is, you know, presents, you know, what's been kind of a, you know, the lasting solution to addressing this problem for, you know, where time dependencies are an issue.
Well, one of the solutions, because after LSTM came up the GRU, which is kind of like you take an LSTM and you take out a few pieces and you make it simpler. But
Okay.
I guess the general idea of just that instead of taking your whole network and just trying to copy it a bunch of times, you have like these individual units that just try to remember information, whether it is an LSTM or GRU or some other memory management unit, whatever.
Awesome. Thanks, Josh.
Yeah.
Any other questions or comments? All right.
Okay, so experiments were performed to evaluate various alternative optimization approaches on problems where where we can increase the temporal span of input-output dependencies. So if it's possible, we should first train on shorter sequences, which really helps, but not many problems have this short-term version. So the goal here was to perform these experiments and measure how the algorithms perform when it's not possible to train using sequences with equivalent short-term dependencies. So experiments were performed with and without input noise and with varying length of input-output sequences. Performance measure criteria. The first one was average classification error at the end of training. So after the stepping criterion has been met, which could be whether either some allowed a number of function evaluations has been performed or the task has been learned. And the second one is the average number of function evaluations needed to reach the stepping criterion. Initial parameters of the network were randomly generated for each trial. The choice of inputs and the choice and the noise for each training were also randomly generated, and the same initial conditions and training set were used for each of the algorithms at the given trial. And the tasks all involved single input and single output at each time step. Experiments were performed on 3 tasks or 3 problems: the Latch problem, the 2-sequence problem, and the parity problem. The Latch problem is the same as described earlier in the simple recurrent network candidate solution section. The second problem is the 2-sequence problem. So just to summarize, the goal is to classify an input sequence of one of 2 sequences when given the first n elements of the sequence, and n varies from pattern to pattern, and noise may be added to the input. And the third problem is the parity problem. This is probably the most difficult problem, and it consists of producing the parity of an input sequence of ones and minus ones. So for example, a 1 should be produced in output only and if and only if the number of ones in the output is odd. And the target is only given at the end of the sequence. The length of the sequence may vary and input may be noisy. And this is a difficult problem because it has local minima, and so it also appears to be more difficult for longer sequences. Are there any questions? Probably not. Okay, so the experimental results. Here we can see how each of these algorithms perform. So the horizontal axis T represents maximum sequence length. On the left side, we can see the vertical axis that represents classification error after training, and on the right, the number of sequence presentations to reach a stopping criterion. So simulated annealing, which is the box symbol, performed well on all problems, but because it's a global search algorithm, it requires an order of magnitude more training time than all other algorithms. And it's also interesting to note here that on the Latch problem, which is the top right, with simulated annealing, training time increases, and as the sequence length also increases. So as we can see here, if T increased, the training time increased as well. The multi-grid algorithm is faster, but it fails on the parity problem, probably because of the local minima. The discrete error propagation, which is the circle, performed reasonably well on all the problems and sequence lengths, and it was the only one, along with simulated annealing, that could solve the parity problem. And it's also much faster, and it seems to be more robust to local minima than the multi-grid random search. The pseudo-Newton backpropagation algorithm, which is this one, performs better than the standard backpropagation, but both algorithms seem to get worse. The performance gets worse when the temporal span of the input-output dependencies is increasing. The time-weighted pseudo-Newton algorithm, so that is the triangle, also appears to perform better than the other two variants of backpropagation, but its performance is also getting worse if we increase the length of the sequence. Any questions here?
Yeah, I'm sorry. What was the x-axis again?
It's described here. The horizontal axis is T, which is the length of the sequence.
Oh, I see. Okay. Yeah, I'm really curious about the final classification error parity problem for square. What is that? Standard backpropagation. It's like, and assuming the y-axis was accuracy, it's weird because it does poorly with low and then poorly with high, and then in the middle there's like this sweet spot where you have 20 long string, and then it just does well. I'm just curious, like, I don't know if you or anyone has any insight into why that's the case, because the rest of the lines, I guess, seem to follow either upwards or some sort of a downwards trend for the most part. There's a few also that go back and forth. I don't know. Just curious.
Yeah, I was wondering if maybe that had something to do with some of the other parameters that weren't discussed in the, associated with the figure.
Mm-hmm. Yeah, something else had to be at play.
And then the discrete error propagation, in that same graph, as well as the one to the right, like some of the, they just stopped testing for longer sequences. Presumably, it just became too expensive, or
it just took too long to run, I guess.
Yeah.
Yeah, it's a weird graph.
Mm-hmm.
It's kind of hard to see what is going on here. Any other questions?
There was another question on the previous slide on Slack. Brad is asking about the units on the y-axis.
On the left side or on the right side? On the left side, it's classification error after training. On the right side is number of sequence presentations to reach a stopping criterion.
So on the left side, lower is better. And on the right side, on the right side, lower is better also.
Yeah.
Okay.
Yeah, it's interesting. In the paper, if you look right under it, they said, for each problem, we chose a suitable architecture for the problem at hand, which means they could all have completely different architectures. So nothing even matters. That's why they're all wildly different, just because a lot of them just have completely different structure. They're just saying, look how hard it is for all these different things, but it doesn't seem like there's actually a control in this experiment.
At least they didn't say for each data point the architecture has changed.
Yeah, that's true. You can see some sort of a trend.
Okay, so the conclusion. Recurrent networks are very powerful in their ability to represent contexts, and they often outperform the static networks. But theoretical and experimental evidence shows that its gradient descent of an error criterion may be inadequate to train them for tasks that involve long-term dependencies. So assuming that hyperbolic attractors were used to store state information, it was found that the system is either not robust enough to input noise or wouldn't be efficiently trainable by gradient descent when long-term context is required. Results presented in the paper hold for any error criterion and not only for the mean square error. So this obviously doesn't mean that it's impossible to train a recurrent network on a particular task, but gradient descent becomes increasingly inefficient when the temporal span of the dependencies increases. So ways to help training could be either using prior knowledge or using the short-term version of the problem. If we have this possibility, we would just present a variety of examples of the input-output dependencies, including short-term dependencies that are sufficient to infer similar but long-term dependencies. And for example, for the Latch problem or the parity problem, if we start by training with short sequences, the system rapidly settles in the correct region of the parameter space. So for better understanding of this problem, there were designed two algorithms, the time weighted to the Newton and the discrete error propagation algorithms. So as the results in the paper showed, the results were encouraging. So there might be a way to reconcile learning with storing. And a good solution to this problem would have many implications for different types of applications for a learning system. For example, language-related problems for which long-term dependencies are essential in order to make correct decisions. So I just want to say that if you haven't heard the interview with Jürgen Schmidhuber, who talked about RNNs and LSTMs, it's really interesting, and you should look it up if you haven't already.
I've got a question. Did you elaborate on the kind of the definition of hyperbolic attractor?
No, it's in the paper, but that's I'm not entirely sure. I don't understand that that part very well.
Does anyone happen to understand that piece of it?
In the paper, it's page 160. It's section 5, 4A.
Section A, analysis.
Yeah.
So definition 2, a hyperbolic attractor is a set of points X invariant under the differential map M such that upside down A sub A belongs to X.
So yeah, for all A, for all A, there exists some, for everything A, there exists some set of points where all the eigenvalues of this differential map of A are less than 1 in absolute value. So what's that saying? That's saying that, so for all A, there exists, let's see. Okay, so there exists a set of points, X, right? X is just some set of points.
Mm-hmm.
We have a differential map. So just there's this function, which is just some mapping, and we're saying it's differentiable. So they're saying it's differentiable because this makes the world easy when we're doing backprop on neural networks. Okay, so we have a differentiable map such that there exists some A, actually for all A in X, for every single point in X, the next statement's going to be true. So for all A that exists in X, all the eigenvalues of the derivative of this map of A. So for each point for each point taken as a function parameter to this map, or sorry, to the derivative of this map, are less than 1 in absolute value. Okay,
so does the eigenvalue of the derivative being less than 1, does that imply convergence in some way?
So eigenvalue, let's see, eigenvalue less than 1. I'm trying to, let's see. It's a criterion, let's see, Yeah, I would assume it has something, yeah, eigenvalues would definitely help with convergence in some way.
Mm-hmm.
I guess that's what this diagram over on the right is. Let's see. Oh, so you see this, like, the diagram on the right, it's like beta and there's this M. It kind of looks like an egg.
Yep.
Yeah. So the domain of A.
They call it the basin of attraction and the ball of uncertainty.
Right. Yeah, I guess if it's less than A, then you're probably, oh wait, I actually, is this part of like exploding and vanishing gradients or something? Or what is this, the bigger picture of, first of all? I just zoomed into the definition.
We're talking about the vanishing gradients here, yeah.
Yeah, I mean, there's a better way. I think there's a much easier way to talk about vanishing gradients than this, I think. So like, yeah, so I guess, so for the, I guess in this scenario, the eigenvalues themselves, then yeah, if they're less than 1, then you're going to help with convergence. But like, I guess in the more general case, when you're doing gradient descent, like you can imagine your neural network. Actually, you know what? I'm just going to like write it on the board. Let's do this. Benefits of that's what we're doing. Actually, I think I know what it is. So f is just some function. Can you see that?
Yep.
Okay, I just want to make sure.
If you double click on the video chiclet, it'll full screen and it's very clear.
Okay. Oh, that's right. I have to. Oh, share content maybe?
No, it's fine.
Oh, okay.
Yeah,
Sorry.
it's totally fine.
Okay, so anyway, so yeah, let's say we have f is some function, and you can imagine that if you have like a neural network, whatever, you're taking like some input x, and this input is going to get modified, and then this is another function of that, and this is another function of that, and it goes on forever. So if you have like f at this layer, I'm going to take f of x. Oh, sorry. I'm going to take, sorry, f, g, h. Sorry, it's really going to be f of whatever g outputs, right? Because these are connected. And then you're going to have g of whatever h outputs. And then of x. Each of these links are basically connections. I'm saying compute h of x. So maybe I'll just do it backwards. That might be a little bit easier. Yeah. So let's do this. So we take x and we put it into h. Okay. H of x. That's just some function. But now we're going to apply g to it. I'm going to ignore all these other nodes because it doesn't matter for now. So we're going to apply g. And then this data flows in, and whatever the output of g is going to go into f. And you can imagine that for really, really big networks, this composition like just grows increasingly large. Like you could have f of g, of h, of k, of l, of whatever. You have a bunch of compositions. And when you start taking the derivative of something that looks like this, you get a lot of multiplications, basically. So what happens is if I take the derivative of this function, then I get f prime of, I guess, if I take the derivative of this, I get f prime of, let's see, oh, sorry, that's wrong. G prime of h of x times f prime of g of h of x, which simplifies down into h prime of x. Sorry, give me 1 second. X. And then basically so on and so forth. And so what happens is you get a bunch of multiplications that come out of this, right? And I guess just accept the fact that if I take a derivative of a highly composed function, a function that has a lot of like inner functions, you get a bunch of multiplications. So then you're going to have your f. And now let's say that the derivative of each of these things was less than 1. Now, let's say the derivative of this thing was 0.9, right? And let's say we're all 0.9. When you multiply all these out, you'll get an increasingly small number. 0.9 times 0.9, that's 0.81. 0.81 times 0.9, you're going to get whatever, 0.72. And the more you compose this, the more you add f's and g's and h's, all your gradients are going to vanish, essentially, go to 0.
Yeah.
Right? So the problem when you have like these really, really big networks is that you're taking all of these derivatives of this giant network, and then essentially you're just zeroing out all the weights. So this can help with, like, if you like add more breadth to your network, you're gonna start adding stuff instead of just multiplying. So like, I didn't do this totally right for sake of explanation, but you can imagine that the gradients over here are just gonna add together depending on how you do the math. But now let's consider the converse, right? So this is vanishing gradients. But for exploding gradients, the logic is the same way, right? So let's say we start with, this is like 1,000, and this is 200, or this is 9. And those derivatives are also gonna multiply, and they're gonna get huge. And with these recurrent networks are usually like very, very big. You'll have like lots of nodes, and they'll be very long, especially in time. And that's the exploding gradients. And really, exploding and vanishing gradients are essentially the same problem, just in reverse. So I assume that's what the eigenvalue math stuff was talking about.
So that analysis section is definitely the most theoretical part of this. And it looks like they're just applying kind of a real analysis or, you know, theoretical analysis to talking about this vanishing gradient problem.
Yeah. Yeah, and it looks...
Nicola?
I didn't really understand the analysis part, so I just tried to summarize the main point there.
Mm-hmm. All right, so it's after the hour. Anything else as far as your presentation goes?
I'm done.
Okay. Awesome. Well, thank you very much for the presentation. Are there any other questions? All right, I see some typing, but I think those are all thank yous and accolades to you. So it doesn't seem like there are any more questions at this time. Thanks once again, Nicola, very much appreciated. And I enjoyed and learned a lot from the discussion. Once again, another appeal to anyone who's still out there and listening, reach out to me and let me know if you can present for November or beyond. We're definitely looking for folks to jump in and help out with the presentations. All right. Thanks, everyone.
Thank you.
See ya.
Bye-bye.
Bye.